Okay, YouTubers, it's Wednesday the 5th of January, first day back at school properly for all my pupils, and there was an awful lot of interest about magnetic fields and how they affect candle flames. Now, I had a very popular video, a lot of you watched it, 2.6 million views and counting, all about how the candle behaves in an electric field, but what about a magnetic field? Now, there's a theory that if we take a strong magnetic field, i.e. a horseshoe magnet or a neomagnet, that you should see a slight difference in the flame. Of course, we need to avoid any implication of me cheating and me affecting the flame just by talking. Now, behind the scenes here, I've got all sorts of little neomagnets. I've got to be really careful, because if you touch them together, they tend to break. So, this is my first one. This is a shoplifter one. So this is one of those round ones that they use for removing the security tags. Now look what happens to the flame. There's definitely effect, isn't there? It sort of slightly flickers. It's wobbling a bit, isn't it, there? I can do this. There's clearly a change. Let's try it the other way around. Change the polarity of the field. That definitely got thinner and longer. Now, the idea actually is really, really simple. So the magnetic field actually enhances the combustion process between the fuels, which are a diamagnetic material, and oxygen, which is paramagnetic. So it's found that a free convection heat transfer from a candle flame may be affected by this magnetic field. It can increase the flame height, the luminosity, the brightness of the candle. Now, I don't have the equipment to test that. I'm not sure I can see a change in brightness, but it looks longer to me. So basically the field seems to increase the concentration of oxygen sort of around where the vapor of the obviously the wax is. Now also the magnetic field enhances the buoyancy of the flame due to that convection current. Now just a little bit for the chemist before I carry on with the physicsy bit. A compound is diamagnetic if all its electrons are paired, and para if the electrons are unpaired. So that's the difference. Now here I've got one of those little cubes. Well, it's a lot of tiny little neodymium magnets, but they're made into a cube. You know what I mean. See what this one does, look. There's definitely a flicker. Flicker, take it away. Changes shape, doesn't it? Maybe a bit longer there. Put that one away there. So we've given that one a go. Again, I'm putting it really carefully to avoid my laptop, my phone and all the rest of it. Now this is a really big horseshoe magnet. Very few people have these, but from schools. So that you can see, look, horseshoe. There it is. Let's see what happens. I'm going to go down. Whoa. That definitely got longer. I'm trying not to burn my hand. Wow. That definitely gets a bit longer, taller. Change the shape. I'll try and do it from the rear. So I'm going to go in to the fields across the jaws. Ooh. There's a definite effect there. I think I'm affecting it now slightly by talking. And I can go closer to it, and then it's got more of an effect. Or this way, I can make it lean in slightly. So that's the big horseshoe magnet. And then the last one, so I got some from AliExpress. I think they cost me about £8, these little Neos. They're quite strong. Let's see what I can do with these. So there's two different ways you can go. So they're attracting, or I can make them repel. Slightly easier. Now that I'm pushing in now, I'm going to have to really push. So we go. Let's put some effort in. I'm trying to push into the flame. I'm definitely shaping the flame a little bit. Look, there we go. It's definitely doing something, isn't it? And I can try it the other way. And then if we go back to the attraction, whoa, nearly. We nearly made it go out. Let's have another go. Can we make it go out? Oh, not quite. And it's gone. There you go. So, candle flame in a magnetic field. Subscribe to Animated Science for more.